Good morning and good evening, everyone. Thank you so much for joining us for today's talk. We're going to get started in a few minutes. We're getting our speaker all set up. My name is Rachel Burson, and I'm Global Programs Director at the Manager at the Robotics Institute and Co-Director of the RISS program. I'm delighted to welcome you to this series where we're going to have the opportunity to explore some of the research of our faculty and scientists across the Institute. If you've heard of the Robotics Institute, if you've had a chance to connect here, one of the things that probably strikes you is just the breadth and depth of the Institute's research. The Robotics Institute was the first robotics institute, the first in the world, founded in 1979. Through a collaboration, and it has gone on to grow to be one of the really largest centers for robotics research, and certainly the largest that we know of that's connected to a university. So bear with us just a few moments as we get set to launch this talk, and we'll be back in just a moment. So I am absolutely delighted to welcome another one of our speakers, and I'll be introducing Dr. John Dolan in just a moment here. The Institute, you'll come, and if you were here, you saw that even the RISS program, which was launched in 2006, we've hosted scholars from over 50 countries. So it really is a global community that comes together to look at some of the most exciting applications and research in robotics. And we'll be hearing in a few moments from Melisa Orta, and I'd like to invite Dr. John Dolan, the RISS director, to say a few words and to welcome Melisa.
Thanks, Rachel. Yeah, it's my pleasure. My pleasure to introduce Melisa. She is a fairly recent addition to our faculty and a very welcome one. And I've also had the chance to speak with her about topics that are related to her research, but not directly the same thing. And they have to do with applying her research to education. And she may have a chance to speak about that today. But the key thing, I think, besides her tremendous enthusiasm and ability, is that she's working in an area which is, in my opinion, not given enough attention within robotics, the area of touch and the sense of touch for robots. So it's a great pleasure to have her here today. And with that, I'll turn it over to Melisa.
Thank you, John and Rachel. It's awesome. Let me just share my screen, hopefully with no more technical difficulties. Yeah, so as John and Rachel mentioned, I'm a new addition to the Robotics Institute. I just joined in September, and I formed the SHRED Lab, which is the Social Haptics, Robotics, and Education Laboratory. And I want to tell you all about some of the work that we do. Our main focus is to do research at the intersection of haptics, robotics, and education, with focus on trying to improve people's lives and through meaningful innovation and community engagement. And so what I want to do is introduce some of the research that we do. And for that, I do feel like I have to define some key concepts, just because a lot of people are simply not very familiar with haptics and the intersection of haptics, robotics, and education. So I'm going to first talk about haptics and what haptics is, if that's okay. And so for that, I want us all to do a little exercise. Please do with me, don't leave me hanging. And so the idea here is that if you can, please just and I know it's hard to see in the camera, so why not, I can move back a little bit. But if you extend your arms out and point your fingers and extend them out, and then try to touch your fingers without looking, try to touch your two fingers above your head. And it's kind of hard to do. I mean, the camera helps us out a little bit, or for some people it might I don't know, mess you up a little bit, but you can do it. And that really highlights the power of our sense of touch. So what's happening is that a lot of people don't really know these, but when you think about touch, you think about maybe your skin or things that burn or pain or things like that. And all of that is part of the sense of touch. The other part of the sense of touch also is our kinesthetic sense, which are actually sensors that are embedded in our muscles, which allow us to understand where our limbs are in space. And they can also sense forces as we are doing motions. So for example, every time I take a step, I don't really need to think about the fact that I'm taking a step, because of all the different things that are happening both in my skin and my muscles. Like in the exercise that we did, my skin is stretching as I'm raising my arm, and that gives my body information about what's happening. Then also my muscles are starting to carry loads, and that also gives information to my body about what's happening. And then finally, at the very end, we use our more sensitive like parts, which are our hands, which have a ton of different mechanoreceptors. And so those are sensors that sense forces, that they're mechanoreceptors. And then they also will kind of say like, oh, there's some contact that just happened. And then other types of mechanoreceptors, they all act kind of like bandpass filters, if you've ever taken like signals and processing or classes like that. And so some mechanoreceptors are going to be like, oh, there's like a new event that happened. And some other mechanoreceptors are going to be like, oh, and that event is still there. And so that's how you kind of detect all the contact and everything that's happening in your body without really having to think about it. So that's the key thing here, is that touch kind of happens without us really having to notice it. And so it's very, very powerful sense. And so because of that, the science of studying the sense of touch and developing things for the sense of touch is pretty complicated and involves a lot of different disciplines. So there's always a lot of collaborations happening. Some of the disciplines it includes is neuroscience, psychophysics, which is an area of neuroscience that's pretty exciting, which I will talk about a little bit about. And then, and also, of course, robotics, because we build devices for it. And so I want to kind of give some framework of where we are in understanding our sense of touch, so that I can give you ideas also of research you can conduct, experiments you can conduct, and novel innovations that there's a ton of novel innovations that still have to happen. And so for that, I'd like to make kind of like a comparison with our sense of sight to understand where we're at. Because our sense of sight is so well understood, and there's so many applications that have already happened for it, right? So let's think about, how does the sense of touch compare with the sense of sight? And for that, the main picture that I want you to have in your mind is this idea of RGB, the fact that we understand how to decompose images into its principal components of light, and that we understand those light components. And from those, we can basically make any image that we want. And so the example is this. So if I am looking at my dog, right, in my eye, what's happening inside, and this is something that we understand very well, is we have 3 cones. I mean, some people have 4, but 1 is repeated. Like the main thing is that we have 3 principal components, 3 sensors that are going to sense light at 3 different frequencies of red, green, and blue. And so these are the cones here pictured. And then, I mean, there's more other complicated processes like rods for light intensity, et cetera, et cetera. But in the main thing, we have those 3 cones that when we look at something, then those will sense light at those frequencies. And then we also understand, thanks to tons of research, how our brain combines the information that those cones are going to send it, and then then now we have like a picture of what we're looking at in our brain. So we understand how that process happens. Because we understand how the process happens very well, we can reverse engineer it. And so now, if I also now take a picture of my dog, I'm actually taking is just, I am just decomposing that image that I have in my brain into actual numbers. So we are decomposing these into just vectors of numbers that will represent how much of R, how much of green, how much of blue I'm going to need. And because of that, now I can just feed those numbers into a computer, and a computer can just process them now. And so because of that, now we have tons of applications in computer vision, movies, et cetera, because now we can just, decompose any image, any sense, any like feeling that we get through our eyes. We can now decompose it into just numbers, and a computer can just process that for us. Now, in the sense of touch, we're not quite there yet. So in the sense of touch is much more fuzzy, and I'll explain why. But if I now, instead of just looking at my dog, I'm touching it, I will say something like, he feels soft and fuzzy. But what is that? Like, what is fuzzy? How do I decompose fuzzy? Like, what is that in numbers that I can just like feed to a computer, so then the computer could potentially render that back to me, right? And so that's what we don't really understand yet. There's a lot of work being done in that. So as I said before, when I started mentioning like mechanoreceptors and things like that, right? So in our eyes, we have like optical receptors or photoreceptors that sense light. In our skin, we have mechanoreceptors which sends pressure and forces, and not just forces normally, so it's not just pressure, but also forces laterally that will deform our skin. And so there's different types of them, and we understand what they are and at what kind of frequencies they operate. As I said, they all operate at kind of different frequencies, kind of like bandpass filters. So one, for example, these Pacinian corpuscles will sense really well vibrations. So if something vibrates, these are the guys that are like getting like, yes, okay, something's happening. And there's others that sense more like slow forces, etc., etc. But then exactly how the information of that gets processed in our brain to give us the different feelings that we feel, and even that language to explain, so that RGB, like what are those principal components? There's some research being done into like, oh, I mean, when you touch something, there's some elements of texture, there's some elements also of heat, which we also sense, there's some elements of adhesion, some friction, some compliance, some stiffness, there's weight. All of that comes into play. And so there's a lot of research being done, like what are even those principal components? The other part of it that's also very interesting is that unlike sight, which I don't know if like a vision researcher is going to come in and like punch me in the face, because this is always a thing. Like vision researchers will tell you like, no, like sight is not just passive, blah, blah. But it is more passive than touch, I will say, because you just kind of sit there and you're looking at things, and sure, you like move your head to perceive the whole space. But in touch, you actually are like actively grabbing your hand and like grabbing an object. And the way you grab it will affect how you perceive it and how it feels. And so there's also that other element, the fact that you're moving around and touching something. And there's research, a lot of very interesting neuroscience research about like what different kind of intuitive movements we make just in order to perceive different objects. Like if we're trying to perceive edges versus if we're trying to just like perceive like material properties like stiffness, we squeeze like these versus like running our fingers through. Those are all intuitive things that we just do, and that's how our body perceives different properties. So you also have to take that into account, the fact that you're moving and you're also applying forces, and then you feel those back also. And so that makes it hard. And then the last thing, well, maybe there's other things that I'm not mentioning, but then the last thing that also makes it really hard is, as I mentioned before, is the fact that it's not just our skin. We also have other sensors in our muscles that are also contributing to everything we're feeling. And so compounded with all of that, what I just want to leave you with from this tiny section is that the sense of touch is very complicated. We still don't understand it quite well, but now I'm going to move into, there's still a lot that we can do, even with what we can, even with the little that we do understand. So let's talk a little bit about what sorts of things as engineers, because I'm an engineer very much myself, we can do and we can develop, and how we can help study more the sense of touch and some applications as well. And so first, just to like a little intro into the kinds of things that we can do. And one is, even with the little that we understand, we can still build haptic devices that will, and so basically a haptic device will be something that interfaces with us through the sense of touch. We all have a haptic device in our hands at all times. That's a phone, which is a very poor haptic device, but it's still a haptic device. It has a vibration motor inside of it, which I said will affect the Pacinian corpuscles, which is one of the mechanoreceptors that we have. And it's good for giving us alerts, etc. I mean, it's not the most awesome thing. It's not going to, feel the same as it would feel as if we like ran our fingers through an apple or something real. But it's still something, like it gives us alerts to the sense of touch. And the sense of touch is very useful for giving us like automatic alerts and things like that without, because as I said, it gets processed very quickly and we don't really have to think about what's happening. And so alerts are good. Other people have tried to do a lot more complicated things. This is an example of something called a kinesthetic haptic device. And so what I mean by kinesthetic is that it's not going to very much affect your skin, or is not specifically targeting the receptors in your skin. Instead, it's targeting the receptors in our muscles. I mean, it'll inadvertently also give you some feelings through the skin, obviously, but what it's trying to do is not very much in this simulation, for example. So a user is holding on to this pen-like tool, and then they're manipulating a virtual dessert, a virtual flan. and so you're not, to the user, it's not going to feel the same as if they like grabbed their finger and just ran their finger through the flan and felt the different moisture and the texture of the flan and the different stiffness of the flan. But they are going to feel kind of as if they grabbed a pen and then with the pen explored the flan. And so you feel the forces through a tool. And that's kind of what a kinesthetic device does. It gives us the forces that we would feel if we interacted with an object, just not all the skin deformation and all of that. These are a little bit easier, I will say, why, to make than trying to perfectly manipulate your skin, just because we still don't quite know how to perfectly manipulate our skin and what that entails. But there are people who are trying. This is an example of one of them. It's a work from Stanford University, in which what they discovered is that they could have some delta mechanism, a little robot that is going to push on the skin in different ways, and that will affect the weight perception. So with something that's maybe not so well known is that when we're holding onto an object with our fingers, the reason why we know how hard to press on it, how hard to grab it, is because of the slip that happens as we're holding it. Our bodies are pretty lazy, and they want to make as little effort as possible. And so when we hold on to something, it starts to slip, and that's when our body knows, like, oh, that's how hard I have to hold it. And so we're always holding objects just enough so that they won't completely slip out of our hands. Now that motion, that slip motion, is just our skin stretching. So what these researchers did is they made a device where it actually actively just stretches your skin. You can see it here coming in contact with it and then moving it sideways. And so then in a virtual environment, they have this simulation, which will come in, here. So the simulation of grabbing blocks, and then they can change the perception of the weight of those blocks by stretching the skin more or less, right? And so again, it's still like, in this simulation, you're not going to feel exactly the way it feels as if you just grabbed a wooden block, but it's still an interesting illusion to do. It's something interesting and cool that, okay, now you can change the weight perception. And so now let me talk a little bit about, so in particular in my group, what we do with all of this and how we try to solve all of these problems that are very, very interesting. So on the one hand, one of the main problems that I see in haptics that hasn't been solved, just the fact that all those devices that I showed, those haptic robots, are pretty darn expensive and hard to do. And so it's hard for other people, aside from engineers, to do a lot of research in haptics simply because the devices are not available. So there's a lot of research to be done. There's a lot of opportunity for applications using the sense of touch, but it's hard for other people to get in the game because the devices, like the first one I showed, which is one of the cheapest devices out there, is in thousands of dollars, right? And then the other device that I showed is very much a laboratory equipment that you have to build yourself. And so one of the, especially for me, because I'm interested in educational applications, so one of the areas that I focus in my group is how to build some of these devices kind of like as cheap as possible and as manufacturable by people as possible. So if you think about, oh, let's make these devices, but all out of 3D printed materials and all from components that you can just buy online, so that, and with everything open source, etc., so that other people can kind of get in the game and also do this type of research. Then the other area that we focus in my group is, as I said before, that the whole tactile aspect of it, the whole how to manipulate the skin, is incredibly complicated because our skin is just so good. And so when you're talking about spatial resolution in our skin, especially in our fingertips, we have, for example, we have mechanoreceptors that can sense different things. So if different point contacts of about 1 millimeter square, right? And so imagine if you try to make a pin array that could act and stimulate each one of the mechanoreceptors individually, then you would need something with a resolution of just every millimeter square. You would need a different pin that could move up and down. So that's the kind of resolution you're talking about. And in terms of forces and speeds, it's our skin is also so good. And so you need very large forces in very small areas. And ideally you would like that all to be wearable so that you wouldn't have to, you don't have to know that it's there, or you don't have to just like come with a huge bulky equipment just everywhere you go, so that you can have experiences in the AR and VR, right? And so another area in my group of what we try to explore is how to create kind of novel materials that will allow us to just research more the sense of touch and render these kinds of forces, etc. So right now, for example, we're experimenting with non-Newtonian fluids embedded with ferromagnetic particles, and then using magnetic fields to actuate in different points in the skin and to be able to render different sensations. And so all of that, like all of the difficulties and everything about doing the sense of touch comes so that we can create just great applications with the sense of touch. Even with the little that we can do, there's been a ton of applications explored. And I think personally that the killer application in haptics has not been discovered just because we don't have the equivalent of a TV for haptics yet. We don't have these actuators that can render just all the feelings that we feel and everything, right? And so, but even with what little we can do, there's been so many advances. For example, in medical training, there's been a lot of different simulations where physicians learn how to operate on patients and how to detect tumors, etc., just with haptic devices. So with a device that will simulate the environment, as opposed to them having to gain the experience, all the experience with patients. Of course, they get experience with patients, but then they can also get practice just from virtual environments. There's also been a lot of interest and research in how to do distant kind of like teleoperated surgeries, so that the idea here is not so much that the surgeon be in a different country or something, which would also be pretty cool if you could get like a surgery with the expert that actually lives somewhere else. But the idea here is that when you use a device like a robot to operate, the killer advantage is that the robot can make tiny incisions, and those can be mapped to big movements. And let me explain. So if you have a tool, right, like a little tool, the tool here, and that's the robot that's right here. So the robot can be operating in the millimeter scale, and then the person that's controlling that, like, because it's just really a controller that's mapping the motions of the robot to the motions of the surgeon, that mapping can be mapped to big motions. So I can be moving like these, like crazy, and the robot can be just moving tiny. And so that leads to very to much faster recovery times for the patient, because if a surgeon has to go in and operate you physically, then they have to make incisions as big as at least to have their hands go in if they have to grab something and touch it, right? But if it's just robot with tools, then it can just be tiny incisions, tiny motions, tiny cauterizations. The problem there with these types of systems is that when a surgeon is physically operating on you, then they're using the sense of touch a ton to know what to do, right? They use, like, you know, when they are cutting you open, like how hard to apply the force, when to stop cutting, all of that information is given to them by the sense of touch. And when now they're only using vision, because they're basically just looking at some goggles and they're just looking at what the robot is looking at, it's really hard to do. It's really hard to know how much to, like, they have some tools that are kind of like how do you say this, like a crocodile, just like grabbing things, right? And like how hard to press on something, how hard to grab it, everything, something that's so natural for us is really hard to do if you're just using your sense of vision. And so that's why there's a lot of interest in how do we give back the sense of touch to a surgeon when they're doing these kinds of surgeries. There's also been a lot of research in rehab. So a lot of the problem in rehab is that when you're rehabbing, I don't know if you've ever been to physical therapy, but the person will kind of show you what you have to do, and then not doing the motions correctly can impact your health greatly because you're using wrong muscles, because you're not actually rehabbing, and then showing you exactly what the poses have to be is really hard. And so haptic devices have been used a lot to kind of like vibrate or give alerts or show people exactly how they're supposed to move as they're doing their rehab. And then there's tons of other applications. There's, you know, in gaming, there's a lot of interest in haptics in gaming, in shooter games, racing games, etc. And then recently also in just trying to improve car safety. So if you had a haptic display as opposed to an optical one where you could just like switch your radio station, etc., and then that would help you just keep your eyes on the road. There's also voice commands that are being explored. However, as I said, haptics is a very automated process. So it kind of happens without us thinking. So if we already have in our memories, oh, like that's the button for the volume, and I can just press it automatically, versus if I have to actually utter the words like Siri, like, I don't know, up the volume, blah, 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 then that's a much higher cognitive load thing, which is why we shouldn't like speak in the phone and drive, because you are actually not really paying attention to it takes your brains a lot to process speech and to understand speech and everything. And so haptics is a much lighter cognitive channel for those kinds of things. And then the application that I want to focus on mostly today, which is the application that we focus in my group, is education. I think that there's a ton of potential for haptics in education, particular when we're babies, when we're young, when we're growing up. We do all of our learning, almost, I mean, not all of it, but we do a lot of our learning through exploring and our sense of touch. And then what is baffling to me is that somebody decided, I don't know who, but somebody decided that this should be the way we should learn. Even though intuitively we never learn like this, we don't do anything like this. We should, this is the way we should learn, just sitting quietly and just kind of taking notes, which is kind of crazy. And because of the way we have decided that our educational models should work and the way we should learn, there's been a ton of research conducted into these different modalities of, like, when we're just sitting down and just paying attention, we're really just using our sense of sight and our sense of hearing to learn. And so there's been a ton of research conducted into what are the best ways to learn using those sensory modalities. But then there hasn't been a ton of research conducted into what about what one feels like. Can we learn what we feel? Like, is there a way to learn through feeling? There hasn't been a ton of studies. There have been a few, and the jury's still out. Like, there's many theories about it. There's some theories that say, actually, I think like you kind of overload your brain if you're trying to like see and hear and also touch. You're kind of just overloading your brain. You may not learn as well. There's other people who believe that no. Actually, you're parallel learning, and it's a different cognitive channel, and you're actually doing something called embodied cognition, which I will talk about a little bit more in just a second. And so there's many options and how to approach this and what to do for these learning through the sense of touch. This is not my work. This is work from the University of British Columbia in collaboration with the Stanford School of Education. But in this case, what they're doing is they're rendering through haptics physical systems. So imagine that you're in your high school physics class, and then you have to learn about springs, and you have to learn the equation, F equals minus kx, and understand what that means in terms of springs and how to combine springs in parallel and in series. And so what they did was they made the simulation where you can play with those parameters. You can drag and drop springs, you can combine them together, and then you can feel them through a very cheap kinesthetic haptic device. And then they studied whether that could help people learn more what those physical systems mean. And so you might think, well, you could also do this with actual physical springs. You could, but then you would have to carry like a ton of different physical springs, and you wouldn't be able to manipulate the equation of the spring and dynamically feel what's happening to that, right? And so that's the big thing. It's like dynamically being able to just feel what's happening with the different physical concepts here. There's other opportunities. This is work that I did with just going to a middle school, and then again teaching them different physics concepts like springs and dampers, and then seeing if kids, through playing with those concepts, could learn the concepts a little bit better. And the work that I'm focusing on right now, what I see as the maybe the big potential of haptics, but that's just my opinion. Maybe not true. But I think there's a ton of potential in mathematics education, specifically because, I don't know, if you think back when you were, learning basic math concepts, and there's really no good representation of mathematics, I feel like. If you're learning about functions, then a professor will tell you like, oh, y equals x squared plus 2, and then they'll draw a graph on the board. And then you're like, okay. And then y equals x squared plus 3, and then kind of looks the same. You're like, I don't know. And so there's not a super compelling way in my point of view to really ground those mathematical concepts. So this is an example of a simulation for trigonometry, in which now a student can play with the trigonometric function and then feel those changes. So they can play with the equation, change the amplitude and frequency, and then feel what those changes are doing. And so I think that, yeah, there's great potential of just trying to see if there are other embodied representations of mathematics. There's a lot of theory that now neuroscientists and education researchers have conducted where they have said, you know what, actually, what we thought about mathematics before, where it was really just like one brain area, and if you were really clever, you could do operations really fast, etc., etc. I mean, all of that's getting debunked and debunked and debunked. And now with MRI studies, etc., now they're finding that actually when we do just the simplest mathematical operation, there's a ton of different brain areas that are coming into play, and that being able to ground those concepts in something is really important. One of those interesting studies is, especially for very small children, as you're starting to learn math, and as you're starting to understand what the numbers mean, like what is a 5, right? Like what does 5 mean? And so a lot of kids, what they have found is that kids who do well in math are those who are able to, for example, ground those concepts in their fingers and have good understanding of their fingers, a good visualization of their fingers, and that they can actually understand numbers to their fingers, which is why now new education researchers and math researchers are telling teachers, like, let kids count with their fingers, like, don't discourage them. That's a good thing, just let them, right? And so with that, we performed a study, for example, trying to understand that concept, and in which we made a device, this device which we called Haptics, but that's not important at all, and which allows students, we kind of mapped, they have these little colorful buttons, and what we did is map each finger to one of the different buttons, and then we made a suite of math activities, and with people from the Stanford School of Education, which are awesome. And then the activities are pretty how do you say, like visual, and they require, it's not just boring like just addition, right? Like they require a lot more mathematical thinking, visualization. And so then what they do is now, so for example, this activity here that you see, it asks them to make 9. So just in any way they can, just make 9, right? And so that makes the student have to think about, like, oh, like what is 9? Well, it could be like 5 plus 4, or it could be like this kid, like 1 plus 4 plus 3 plus 1 plus equals 9, right? And so the way they answer these activities is through their fingers. So you have your 1 finger, your 2 finger, your 3 finger, etc., etc. And so it makes children be very conscious. You can see it in this comic book. Like if you're just asking the question, what's 3 plus 5? Then it makes them have to be very conscious about exactly what they're doing and what finger is going to represent that number, and that number has a physical representation in their bodies. And so what we did was a study where we grabbed, it was 120 students, and about half of them did the activities using the buttons and Haptics throughout 8 weeks, and then half of them did the activities just using a laptop computer. And then we did see huge improvements in math learning with the kids who did the activities using the buttons. And there's still a ton of research to be done, like exactly why, but we believe it's because this conscious cognitive representation of numbers just grounds mathematical concepts for them and allows them for a 5 to not just be an abstract number, but to be something that they can actually feel. And so in my group, we're still doing a ton of research in that space. We're now working, for example, having a haptic glove where you can manipulate functions in space, as if they were clay. Iki's working on that. Iki's working on that right now. And so, yeah, and the idea again is, how do we ground all these very abstract concepts that we just have no real representations for, so that math becomes just, better, and it's not so scary for people. And yeah, and with that, I will take any questions, and I can stop sharing my screen.
Okay, wonderful. Thank you so much, Melissa, for that introduction and overview of your work and the impact of that area. So we're going to any of the students that we're handling questions in 2 different ways. One is that anyone who's joining us that's not in the room right now will be able to use the link that was provided to ask questions, and we'll curate that and share those with Melissa. If you are one of the scholars and you would like to unmute, you can do so or add a question directly in the chat. So we'll give everyone a moment, and then we'll get started. Okay, so I'm gonna kick us off with the first questions that came in. And it says, do you feel like high school should adopt robots into their STEM curriculum? And what's preventing educational robots from being a more widespread in the classroom and accessible?
Oh, thank you. That's a great question. So I'm going to be cautious with this because I have very strong opinions on current educational robots. But I will say yes, definitely, but thoughtfully. So I say that the solution is not just to grab a robot that kind of moves around. There's a lot of these, right? There's a robot that kind of moves around, and you just like put in a kid's hand. And it's like, you know, program that and learn, and just go away. And like, nah. The idea is that's why it's very important to involve teachers and community members and educators into how you make your curriculum. Because what I've learned is that it's really more about, okay, what are uniting concepts is always a good thing. So what are the actual concepts, the actual learnings that you want people to have? So the usefulness in programming is not just learning how to program. It's not actually like writing a for loop. It's understanding the logic behind it. Is in you do things in one way. Now the computer has a different set of rules for how they can achieve different tasks. So you putting yourself in the mindset of that computer and actually learning how to tell the computer to do these different tasks is very, very useful. And also understanding that there's many different ways, there's many different languages that computer might be able to interpret. And that's also very useful. Understanding that you could potentially program the same thing using linear algebra. You could potentially program the same thing using just instructions. And what are those instructions? You could program the same thing using just digital logic, using just ones and zeros, right? And so understanding all of those and uniting all of those, that's very useful. So I would say a robot that you program to move around using those concepts, that's very useful because that actually leaves you with something. Just like giving somebody a robot in their hands and just like programming a go and just learning one set of instructions without the background of what actually is, that doesn't really translate very well. Because at the end, you're never going to be able to go to high school and teach somebody this is exactly what you need to know to succeed in life. The goal is to teach how to learn, like that. That's the main goal, and so that should be very much thought of when you're developing curriculum. And so I believe that good collaborations between education researchers and roboticists, and to put robots in the hands of teachers, that would be great. And also I think another thing is also to involve the teachers. I think that one of the big roadblocks is that a lot of the times these robots, etc., are designed without teachers in the loop. So when you design it, then they don't really know how to use it or what to do with it, or it doesn't have the features that they want. And so then that's a big barrier for teachers to adopt a new technology. And of course, we could talk for like 3 hours about, the American education system and how badly teachers are paid and etc. And you just ask them to do one more thing and they're going to explode.
So a couple more questions. We have about 10 questions. So I'm going to dive into the next one. Have you or any other researchers looked at studying children who learn through Braille versus sight reading to look at the impact of touch on learning?
That I believe there are. I myself haven't done it, but it's an area that I'm very interested in. Like, luckily, I'm just starting out. But yeah, one big thing that I've read that is a big difference is that, especially for people who are blind or have some I don't know, I forgot the word in English, but sight impaired or something. Mathematics is very visual. The way, if you think about linear algebra, everything, all of our representations of mathematics are visual. And so for them to be able to actually even do math operations, so having a haptic math language, that would be huge for them. Yeah, and it's not necessarily Braille, so we shouldn't just try to just like carve out our version of the world and try to represent it for them in a way that they can see it, right? So it's not just about like grabbing a map and just like making features high so they can feel it. No, it's about how to actually, like, again, in collaboration with them and when with researchers of the blind community to understand like what would be a useful representation of a graph for them. It probably doesn't have to have spatial. It's probably not spatial. We need to think about like what's useful for them. But yeah, that would be great.
Fantastic. Thank you, Melisa. Has any research been done in predicting the feel of a surface? For example, soft, fuzzy, rough, based on the data from sensors by using models like neural nets?
Yeah, that's not work that I've personally done, but there's another researcher, Winston Yuan, here in the Robotics Institute, because I mostly work on tactile actuating, and she works on tactile sensing and has done some fantastic work. So what she does is she grabs a camera and then a gel, and then she then fits models to how that gel deforms as it gets pressed against different surfaces, and then through neural networks predicts what that object that you're touching is. Yeah, she does amazing work. You should check her out.
Okay, fantastic, fantastic. I'm going to try to get through all these questions.
Yeah, I'm so sorry.
No, they're coming in fast. They're coming in fast in this external system. But we really also want to hear about your journey, right? And so one of the questions that I'm going to ask you as we wrap up is going to be your advice or guidance for this group of students. So we have students joining us. I'm looking at the different registrants from at least 15 countries right now. And that's awesome, right? And they're looking at what are their opportunities and next steps. And if you could go back to that time where you were about to consider graduate school, what would you say to yourself then? What would be the best advice, right? Because when we look back, it's always like, oh, I should have done that, right? And so I'm going to ask you that, but a few more of the questions that are coming in. How does the sense of touch help a robot to learn? Does it remember its motions?
That's a really good question. So that's also myself, I haven't explored this so much, but there are a ton of other researchers because right now the way robots move again is through the sense of sight. So they give them a lot of cameras, and really good cameras, and then they're like, move. But we don't move like that. We move just by the sense of touch. So how do you give the sense of touch to a robot? Is a very open question that right now is very limited by the technology that's available. So there are some like force torque sensors that are so expensive, and their researchers are trying to put them in the joints of robots. But again, and that's where Winston's work also comes in, because she is trying to put like tactile touch sensors on robots. But yeah, it's a very open question. There isn't a good solution right now, and it's another great area of research.
And there's several questions that are around that area, Melisa, that are about haptic robotics. Like, when are they implementable? What needs to happen, to make that possible, right? And that's something that you touched upon in a moment. But anything else that you'd like to add to that?
Yeah, there's right now basically like size constraint is very large, and how many pixels, as I say, in our skin, we have thousands of mechanoreceptors in a centimeter square area, right? And right now, the sensors that are out there that we can come up with, if you think about your touch screen, which is just an amazing piece of engineering, it really can detect, like I have 4 fingers on it, and then that's it. It can't detect like, oh, there's a pin touching it versus, and so just working more on those types of sensors is really the bar to cross.
Cool. In another question, in the study you just talked about, do you think children will need to have a sense of touch when doing math in the future? How could this be a detriment? How could it be a positive?
I hope they do. I hope that we translate to a more kind of constructivist type of learning, in which you're actually exploring concepts as opposed to somebody kind of trying to flood you with a skill. It's more about you constructing your own and learning and the representations that you can give to yourself so that the concepts make sense. And so I hope that they would. I know that there's a few people with some diseases where their sense of touch is impaired. So we of course have to keep those people in mind when we are thinking about how to do a more constructivist touch approach to education, but I only see positives, really. I mean, they might get louder. I don't know, like if you're playing around, but I don't know.
So you said haptic sensors in our hands are poor. What are you modeling mechanical sensors after then? What's the baseline?
In what do you mean, like in our no, our sensors are really good. Are the sensors that we have are really good. The sensors that exist right now, where we try to mimic what our hands can do, are quite poor. Yeah.
Okay. And let's see, they're coming in so quickly, Melissa. I'm so sorry. Okay, so you said, as you told at the start of the talk, that vision systems within the eyes decode the light into RGB constituents. In a sense, it is quantifiable. So is it possible to quantify touch by modeling mechanical receptors, etc., to map certain quantities?
Yeah, and that would be the goal. It's exactly what we're gonna do. There's still not as much of us understanding kind of the map between. So if we understand that, for example, mechanoreceptor X, right? Let's say the Pacino corpuscles sends frequencies at around 250 hertz, right? And then, but we don't quite understand how, from us sensing that, we come to sense what we feel when we touch a piece of wood, for example. Does that make sense? So we don't really have the language and how those signals come together in our brain to give us the sensations that we feel. And so that's the piece that's really missing for us to be able to say, yeah, like if we had a measure, and let's say one measure was friction and one measure was fuzzy, right? If we could say this signal is going to represent, right, like this combination of signals is going to represent 255 of fuzzy and 20 of friction, etc. Then we can do that, but that's still missing because we don't quite understand it.
Absolutely. There were some questions that are around communications, whether language or sense of knowing through that. Would it be applicable to invent a system of haptic language to convey certain ideas, even complicated ones, just like natural languages for communication between people or programming languages for human-machine interaction?
Yeah, and that's very interesting because there's a guy, and I forgot his name, who just, I mean, it's a wacky guy, but awesome guy, who made a vest because he wanted to go running and just like read the stock market as he was running. And it's just a vest of just tactile actuators. It's just like vibrating in different places in his body. And he taught himself a haptic language to just be able to run around and like read the stock market as he was running around. So it's definitely possible. Facebook is actually investing in this area of how to give like haptic icons and what would be a good haptic language, right? To just like actually like poke somebody or something. So yeah, it's, and there are other researchers. I should mention this person, like Heather Culbertson from USC, is also researching in this space, and she's awesome.
Excellent. Melissa, how are the different math functions being uniquely mapped to a touch aspect? That's one of the questions.
Yeah, that's a good question. So the way I'm approaching it right now is I'm not trying to map each function to a particular feeling. It was more about what I was trying to do, which is also a great idea. Maybe we should explore that too. But what I'm trying to do is more, imagine if you could manipulate some sort of clay, like Play-Doh in space, and as you were moving it and it would start representing different functions, then you could also see the equation. So now it's more about the motion for me right now. So it's more about, if you do these, then that's a square function, and if you do that, that's changing a linear function, and it's trying to map those motions to the function. But you're right that there might also be a great way to map different types of just haptic signals to different mathematical concepts.
What are the next steps for your work on the use of haptics in education? That is a passion area of yours.
Yeah,
So yay.
that's a great question. Oh, there's just so much. So I want to say I really wanted to get that question that I received about the blind users. I really want to get into that area. I would love. I mean, I'm sure it's not going to be like just me at all, and it might not be in my lifetime because it took thousands of years for us to come to know mathematics as what it is. but it would be unbelievable if I could contribute a little bit into what a new mathematical language that did not involve a spatial representation of things and instead of tactile representation of things. So, and what makes me, what gives me hope is, you know, things that are non-Euclidean geometry, things like knot theory and topology and things like that, where the representations can be different and you can do operations and it doesn't have to be in Euclid's world. It doesn't have to be a visual representation. So we'll see.
Okay, well, wonderful. We're going to take the last question, and apologies for not being able to get to everything, because we want to shift over and talk a little bit about Melissa's journey and such. So our last question, do you think reinforcement learning can be applied to the field of haptics and robotics? Why and how and what excites you?
Yeah, I think it could. So here's my feeling is that my problem with reinforcement learning is you grab a certain set of inputs and outputs, and then you say, I don't really know what's in between, so I'm just gonna put a black box in and we'll see what happens. And it is a great way to solve a ton of problems. It might even be the way that our brain solves a ton of problems. With the haptics problems that we have right now, there are physics models for it though. So you can just look at the physics and solve problems through the physics. Some problems in human behavior that might be really good to use reinforcement learning. And every time you make any haptic device or you do anything with haptics, you have to do a combination of things. One is understanding what the device and its capabilities are. The other thing is understanding what the device's capabilities are from the human perspective. And that's really hard to analyze. There are some psychological tests for that, but that's where maybe more of reinforcement learning might come in play. Yeah.
Phenomenal, thank you. So we've had a chance to talk a little bit about your journey, right? Like your journey and your career and your interests, and I wonder if you could share with us, how did you get first interested in STEM, and what helped propel you forward?
Yeah, so, so I would say as with anything, it's more of a story of luck than anything else. And like I will challenge anybody who says that they're a self-made person. I mean, for me, mostly, I mean, to be honest, all my life I wanted to be like, you know, in the arts. That's what I wanted to do. That's what I loved. And it wasn't until I was in high school and I had a computer science class. And then in the computer science class, imagine computer science class in Mexico in the 90s. Like, I'm pretty old also. And so it's no computer almost involved, just like paper, you know? And so then, and in that, and the professor gave us a challenge of an algorithm to write up. And he gave it to everybody. And then he said, oh, if you can do this, you should consider a career in computer science, right? And so I actually like worked on it and did it. And I was actually the only person who did it. And I'm not really thinking about skill. Like, I was also very much a nerd. You know, in Mexico, it's like not cool to study and stuff, right? So, you know, so probably just because I was so nerdy. But the thing is that I was able to do it. And then when I handed it in, the teacher was like, but you're a girl. So, and then I was like, okay, I guess I'm studying computer science now. And so that's why I started. It was miserable. It's the worst thing that's ever happened to me. I failed miserably. I went without knowing anything into computer science. Everybody knew everything in the classes. I knew nothing. I barely even turned on a computer to write, because that's what I like to do. I like to write essays, you know. It was miserable, failed out. and then went into electrical engineering. So I once I was like just failing, then I talked to the people there and I was like, what else can I do? Because this is not working. And then they recommended electrical engineering. And I thought that might be good because the playing field was a little more even. It's not like people back in the 90s were just building circuits in their backyard. So at least everybody was almost, you know, the same. And so then that was better. That was a lot better. And then I did succeed at that after a lot, because I didn't have the background. And it's hard. And then from there, I got the opportunity to go actually to Germany to work for a little bit in between. And then that's where I learned. I didn't know in Mexico about like PhDs and masters. Like in my family also, nobody really was an academic, and so it was pretty dismissive about academics. It was like, oh yeah, those people don't work, you know. And so in Germany, I was like, oh yeah, you can actually do work and like be an academic. And And so that's what got me interested into graduate school. Yeah.
I love that. I love that. Melissa, so we have just a few moments left together, just a few minutes. When you think about robotics and you think about the impact of that robotics is having and can have, can you speak to that and share your thoughts?
Yeah, I mean, so in an ideal society that where we actually care for people, then I would say the great potential for robotics would be to basically do all of the menial tasks for us, right? Like if we were actually interested in caring for people, robotics can do the tasks that nobody wants to do, that like the tasks that don't require any imagination, that honestly I believe nobody should be doing. So I think that that's a great potential, the great potential for robotics. Yeah.
Wonderful. This has been absolutely fantastic to have you join us today. And we look forward to, continuing to follow your work. And I'm just want to, again, thank you from the entire team, the scholars and those that are joining us from all over.